Today we will just give an outline or the definition of another law of large numbers, which is known as strong law of large numbers. We have already seen that weak law of large numbers, but now we should move on to develop or to define strong law of large numbers. Now, another issue is that when I say that there is another law of large numbers which is called strong law of large numbers, we need to understand that this is actually in relation to what type of convergence. As we know that weak law of large numbers is basically dealing with probability convergence in probability. So, strong law of large numbers is actually dealing with the almost sure convergence. Now, so naturally we have to give some laws and we have to produce the proofs, but for the moment instead of giving the proofs of the strong law of large numbers, because these proofs actually require a few results. So, today we will discuss two very important lemmas which will be used extensively in order to prove the strong law of large numbers. Now, I should mention that the strong law of large numbers are actually due to Kolmogorov, and the lemmas are, one is directly coming from the real analysis and another is from the probability theory. Now, the real analysis actually gives us the lemma which is known as Kroneker's lemma. It actually relates two sequences of real numbers. One is convergent and another actually increases to infinity, and we take some sum of products of this number divided by another quantity. So, we will discuss the convergence of a particular quantity which is a function of the two sequence of real numbers. So, that gives us the Kroneker lemma, and there is another lemma which is called Moments lemma, that is due to Loewe, the famous probabilist. This lemma is very important in the sense that sometimes it might be difficult to directly calculate the moment of some order for a particular distribution or to show that existence of the moments of a particular order. Now, in order to do that, we can just bound this some general order moment, say rth order moment for r greater than 0 by two quantities which is given in terms of the probability. So, that here we are trying to give a bound of the moments in terms of a function which is a function of the probabilities or in terms of the distribution function of the random variable. So, this is extremely interesting to see that how these moments can be bounded by the probability and the distribution function, and obviously another function is there. So, this is extremely interesting. Another thing which I would like to mention at the very beginning, that try to understand not only the proof, but also the technique of the proof, the line through which we proceed to provide the proofs. That is also extremely important, and that would be a very interesting and very good learning experience to understand the technique and the tools that has been used in proving these two lemmas. So, our main objective to discuss a strong law of large numbers mainly due to Kolmogorov, but before doing that we need a few important lemmas from real analysis and also from probability theory. So, let us first give you a flavor of what is the meaning of strong law of large numbers. So, it can be considered as a definition like a sequence xn of random variables, they are all L1 random variables, is said to obey the classical strong law of large numbers. We abbreviated this thing as SLLN. Just like the weak law of large numbers we call WLLN. Similarly, this strong law of large numbers, if 1 by n summation I equals to 1 to n, xi minus expectation of xi goes to 0 almost surely. So, remember one thing, weak law of large numbers is basically convergence in probability, and here we consider strong law of large numbers is dealing with convergence almost surely. So, this is the important difference between these two laws. There are a few strong law of large numbers due to Kolmogorov, one for independent random variables, and one can also state an SLLN, a strong law of large number, which is only for independently and identically distributed random variables, are commonly known as IID random variables. So, our main objective is to prove or discuss this Kolmogorov's strong law of large numbers, but before that, this talk I will devote only to prove two extremely important lemmas, one from analysis, real analysis, and another from probability relating to moments of a distribution. So, one lemma from real analysis, this is nothing, this is called famous Kroneker's lemma. So, now remember, this is a pure, this result is purely based on real numbers. So, consider two sequences of real numbers, one is an, another is bn, obviously n greater than equals to 1. Now, these two real number sequences, we impose two conditions. First one is that this sequence of an, summation an equals to 1 to infinity converges, and bn is another sequence of real numbers where bn is an increasing sequence of real numbers, bn is increasing. So, under these two conditions, we have to prove that 1 by bn summation k equals to 1 to n bk into ak goes to 0 as n goes to infinity. That means, we consider a sum of product of the numbers from two sequences, two real number sequences, which is nothing but ak into bk, and if we divide, they take the sum, there is a sum k equals to 1 to n, and divide this by bn, then this entire quantity will go to 0 as n goes to infinity. So, one can think that this summation bk kind of weighted sum, but there is in the device or in the denominator we take just bn. Now, the proof of this lemma requires only manipulations and some simplifications, and again as we have seen in many other results and lemmas and theorems, that this also involves some particular techniques. There is nothing special about this thing, but some manipulation is required. So, we have to be very careful while proving this, and at the same time this is a nice learning experience for us to learn several techniques that has been applied in real analysis as well as in measure theory and probability. So, just look at the, try to understand the technique applied, a very critical technique, very interesting technique and very special at the same time, and we can use this kind of technique anywhere we want. So, since it is given that summation an converges, we can immediately write that Sn equals to the partial sum summation k equals to 1 to n ak, this converges to some quantity, let us call it S. So, Sn converges to S because summation an equals to 1 to infinity converges. Also note that S naught equals to 0, or we can set S naught equals to 0. Then let us consider the main quantity in which we are interested, that is 1 by Bn summation k equals to 1 to n Bk into Ak. Now, this is equals to, let us keep 1 by n outside as it is, and inside the sum Bk we just replace Ak by Sk minus 1, because we have defined Sn as summation ak k equals to 1 to n. So, ak is the sum of the numbers up to the kth term minus sum of the numbers up to the k minus 1th term. So, this is just a trick to write it down. Now, just split this thing and we get 1 by Bn in summation Bk Sk k equals to 1 to n minus summation Bk Sk minus 1 k equals to 1 to n, and just by little bit of change of suffixes we can write this thing as 1 by Bn summation Bk Sk. First term remains unchanged, second term is also the same, but we are writing in a different way. We just replace k by k plus 1. So, we get Bk plus 1 Sk k equals to 1 to n minus 1, and this is equals to 1 by Bn into Bn Sn, because if we look at these two sums, the range for one first sum is k equals to 1 to n and the range for the second sum is k equals to 1 to n minus 1. So, if we just separate the nth term in the first sum, that is nothing but Bn Sn, and if we keep k equals to 1 to n minus 1, then we can just take common, or we can take this thing together as minus summation k equals to 1 to n minus 1 into bk minus bk plus 1 into sk. Now, this bn cancels in the first term. So, all we are left with equals to summation equals to Sn minus 1 by bn summation k equals to 1 to n minus 1 into bk minus bk plus 1 into sk. Let us call this equation 1. Now, remember one thing, that here there is no inequality, everything is equal, and just little bit of adjusting variables in terms of another variable, like adjusting rather real numbers n in terms of Sn, we can write this thing. So, we are writing this main quantity 1 by bn summation bk ak in terms of sk, or the partial sums of sequence of real numbers an. Now, we can again write 1 by bn k equals to 1 to n minus 1 from the previous page, bk minus bk plus 1 into sk. We can write this just by adding and subtracting, just by adjusting one term, which is s. S is the limit of Sn, we have already seen. So, we can write this thing equals to 1 by bn summation k equals to 1 to n minus 1 bk minus bk plus 1 into sk minus s plus s is actually constant because it is independent of k. So, we can take this s outside. So, s by bn plus into k equals to 1 to n minus 1 into of bk minus bk plus 1. So, here we just add s and subtract s and then take out s outside, because s is completely independent of k. Now, look at the last term, s by bn summation k equals to 1 to n minus 1 into bk minus bk plus 1. Now, if we break this summation, then one term will cancel with the one term in the next bracket, next term. So, ultimately what we get is s by bn into b1 minus bn. Now, as b1 increases and increases to infinity, in fact, so b1 by bn goes to 0 and bn cancels out. So, we are left with just minus s. And what about the second term? Second term is basically, what about the first term, because this is what we have done in the second term. Now, let us consider the first term. Now, first term is 1 by bn summation k equals to 1 to n minus 1 bk minus bk plus 1 into sk minus s. Now, again just by simplification we can immediately have this minus s, actually this minus s into bk minus bk plus 1, and sum over that goes to minus s, as we have just seen, and the first term goes to again s. So, basically this entire thing goes to s minus s, which is equals to 0 as n goes to infinity. So, from 1 we have 1 by bn summation k equals to 1 to n bk ak, which is equals to Sn plus 1 by bn into k equals to 1 to n minus 1 summation bk minus bk plus 1 into sk, which goes to s minus s, which is equals to 0 as n goes to infinity. So, that is basically our Kroneker's lemma, that under the two conditions, that summation n converges and bn increases, and in fact increases to infinity, we have 1 by bn summation bk ak goes to 0 as n goes to infinity. So, this proof is extremely easy, except that you have to manipulate with the several terms and just finally come to the right term, so that you can get nice limiting values. The second important lemma is in probability theory, which is known as moments lemma due to Loeb. So, let us define a random variable by x, and qt is some probability modulus of x greater than t, which is equals to 1 minus ft equals to f bar t. This is the standard notation. Then for every r greater than 0 and x greater than 0, we have x to the power r summation n equals to 1 to infinity q of n to the power 1 by r x, which is less than equals to expectation of modulus of x to the power r less than equals to xr plus xr into summation n equals to 1 to infinity q to the power q of n to the power 1 by r x. So, what is the meaning of this lemma? This actually gives us again an upper bound and a lower bound to the rth order absolute moment of the random variable. Another important thing is that if we look at this upper bound and the lower bound, they are both in terms of the same quantity. Only in the upper bound there is one extra term which is x to the power r, and the restriction on x and r are they should be both positive. That is the only restriction. So, this lemma is a very general lemma, very general result that relates to rth order absolute moment, that actually gives the lower and upper bound of rth order absolute moment for every r greater than 0, provided obviously the moments exist. Let us prove this result. Now, what is expectation of modulus of x to the power r? That is nothing but 0 to infinity t to the power r dp of mod x less than equals to t. So, this is the probability measure induced by modulus of x random variable, which is equals to minus 0 to infinity t to the power r dqt, because if you just check what is the relation between qt and pt. So, if you take the d of that, it is just minus of d of q. Now, we can immediately write this thing. This is a standard technique in integration theory, that we are splitting this integral as summation minus summation n equals to 1 to infinity and the piecewise integral, that is integration over within the limits n minus 1 to the power 1 by r x to n to the power 1 by r into x of tr, same thing tr dqt for x greater than 0. So, we are considering the piecewise integral first and then consider the sum over n equals to 1 to infinity. So, this will cover the entire range, and this is exact. So, that is why we put equality here. So, let us call this as equation 1. Now, by the standard mean value theorem of integral, and noting one interesting thing, that 0 less than equals to qn. Now, qn is decreasing because qn is 1 minus pn actually. Pn is nothing but the kind of distribution function. So, it is increasing or non-decreasing. So, we can have qn is decreasing or non-increasing. Then we have minus of integration n minus 1 to the power 1 by r x to n to the power 1 by r x t to the power r dqt, which is less than equals to using mean value theorem of integral, less than equals to n x to the power r into q of n minus 1 to the power 1 by r x minus q of n to the power 1 by r x. Let us call this equation 2, and another bound we have minus of integration n minus 1 to the power 1 by r x to n to the power 1 by r x t to the power r dqt, the same quantity is bounded below by the quantity n minus 1 x to the power r into the same quantity, that is q of n minus 1 to the power 1 by r x minus q of n to the power 1 by r x, and we call this equation 3. Now, if expectation of modulus of x to the power r equals to infinity, then the proof is obvious. There is nothing to prove, this is pretty trivial. And if expectation of modulus of x to the power r is less than infinity, then immediately we have x to the power r n capital N into q of capital N to the power 1 by r x goes to 0 as capital N goes to infinity. So, this is just from the standard probability theory, because this is 1 minus distribution function and within that there is capital N. So, as capital N goes to infinity, this goes to 0. So, from 1 and 3 we have expectation of modulus of x to the power r greater than equals to summation n equals to small n equals to 1 to capital N, n minus 1 into x to the power r into q of n minus 1 to the power 1 by r x minus q of n to the power 1 by r x. This comes directly from 3, which is exactly equals to n equals to 1 to capital N x to the power r into q of n to the power 1 by r x minus the whole quantity minus n minus 1 x to the power r into q of n to the power 1 by r x. Let us call this equation 4. Now we see that n into q to the power n into the power 1 by r x goes to 0 as capital N goes to infinity, then the right hand side of 4 goes to summation n equals to 1 to infinity x to the power r q of n to the power 1 by r x, thus which proves the lower bound of Moment's lemma. Now we can apply more or less same technique to prove the upper bound of the lemma, to show the upper bound of the lemma, that is, if summation n equals to 1 to infinity q of n to the power 1 by r x less than infinity, then again we know that n into q to the q of n to the power 1 by r x goes to 0, because n is inside, and as n goes to infinity q of infinity goes to 0. Then expectation of modulus of x to the power r is less than equals to limit capital N goes to infinity. We are applying more or less the same technique as we have just did. That is summation n equals to 1 to capital N x to the power r into q of n minus 1 to the power 1 by r minus q of n to the power 1 by r x, and which is exactly equals to limit capital N goes to infinity x to the power r into 1 plus summation n equals to 1 to n minus 1 q of n to the power 1 by r x minus capital N q of capital N to the power 1 by r x. And again we know that as capital N goes to 0, q of capital N to the power 1 by r x goes to, as capital N goes to infinity, then q of capital N to the power 1 by r x goes to 0. So ultimately limit of this quantity is exactly equals to x to the power r into 1 plus summation n equals to 1 to infinity q of n to the power 1 by r x. So this gives us the upper bound of the Moment's lemma. Now also I have already mentioned that they are both basically in terms of more or less the same quantity, only one additional term is that x to the power r is attached to the right hand side. Now let us conclude this talk only mentioning two strong law of large numbers due to Kolmogorov. One is Kolmogorov's strong law of large numbers for independent random variables, which states that if x1, x2, xn are independent random variables with expectation of xk equals to 0 for k greater than equals to 1, and summation n equals to 1 to infinity expectation of xn square by n square is less than infinity. So this is an important condition. Then we can show that, or Kolmogorov's SLLN claims that Sn by n goes to 0 almost surely as n goes to infinity. Now there is an analogous version of this strong law for IID random variables, that means random variables which are independently and identically distributed random variables. Let x1, x2, xn be such random variables, then and define Sn by n as 1 by n summation I equals to 1 to n xi, then Sn by n goes to c, which is less than infinity almost surely if and only if expectation of modulus of x1 less than infinity and c equals to expectation of modulus of x1. So basically this gives a characterization of almost sure convergence in terms of the existence of first order moment, and in the strong law for independent random variables we assume the existence of second order moment, but in the case of IID random variables we only need the existence of first order moment. So we have learned two important lemmas which will be used to prove strong law of large numbers later on. We will discuss that proof later. But these two lemmas, as I have already mentioned, one from real analysis which is known as Kroneker's lemma, that relates two sequences of real numbers. Another lemma that is called Moment's lemma or due to Loew, that is from probability theory. And this, the interesting fact about Moment's lemma is that it gives a bound to the rth order absolute moment of a random variable in terms of a quantity which is nothing but the distribution function, which is in terms of the distribution function of the random variable. So that is very interesting. Another point which I have just outlined or pointed out, but I would like to emphasize very clearly that we have used some nice simplification and manipulation technique in order to prove this Kroneker's lemma as well as Moment's lemma, both these two lemmas from two different perspectives. But these techniques and tools are very important and they are very easy. The thing is that they are very easy, but you have to be very careful when you apply these techniques. And these techniques are extremely powerful, very easy, is very like class 7 or 8 algebra in some cases, but they are extremely important, and from through these techniques we have actually discovered many interesting things, as we have already seen while in the course of proving these two lemmas. So, along with the lemma and its proof and its implication and importance, I also would like to emphasize that our take home message should also include the technique and the tools and the manipulation, how one can manipulate, how one can simplify the complicated expressions, and finally we achieve the main result. So, that would be a nice learning experience, and we can apply this technique and tools in many areas in mathematics, statistics, probability, and many other areas.